Great. Okay, so we're gonna jump about. I was doing a calculation, something like 12 or 15 orders of magnitude in scale from zircons to plates, and this particular project, some of you have been following, is an attempt to understand tectonic processes in greenstone belts by comparisons with possible modern analogs. The fact of the matter is we're learning a hell of a lot more about modern oceanic crust from the ancient analogs than we are the other way around, but maybe some of that'll come out here. So the project is being run by a large team. I'm just the representative of the team, and they're spread across a couple of continents, working in trying to characterize different types of oceanic crusts that have never been mapped before, and that's been one of the major challenges of the project. The key partners are shown here. The really key partners are the German Marine Research Institute, GeoMar, and more recently, NSERC funded CREATE project called IMAGE, which is helping us do some of the required training in critical training in seafloor mapping. The project is really highly leveraged by our overseas partners who are basically funding our marine work, our research cruises, which obviously are beyond the scope of most of the projects we can fund here in Canada. The context or the underpinning of the work is this well-established relationship between crustal growth, pulses of crustal growth, and the formation of mineral deposits. The problem in this relationship is that it looks fine at a certain scale, but it's somewhat crude, and we're still trying to understand the actual drivers of pulses of mineral deposit formation associated and mineral endowment associated with these pulses of crustal growth. And the challenge is to get the right time and space scales to make those assessments, because there's still rather large gaps between the pulses of crustal growth and the episodes of ore formation, whether you're looking at what's happening in the modern ocean or, of course, in the geological record. But the modern ocean offers us this one thing that we can do that is difficult to do in the geological record, and that's to look at things almost in real time. And we've chosen an area of the crust of the globe in the Indo-Australian margin, which is the location of some of the fastest growing crust on Earth. And so we can observe a lot of the large scale processes that we think might be responsible for this relationship between mineral deposit formation and crustal growth. This area, of course, is characterized by some of the highest predicted mantle temperatures on Earth today. And also, obviously, it's the location of some world-class copper and gold deposits. To study the processes that we needed to study, we needed geological maps. And so we set out to create some of the first geological maps of the Indo-Australian margin underwater. This turned out to be a long journey of learning, because we had to teach ourselves how to do it. Nobody had been making maps like that before. And we now have a training program, as I mentioned before, the IMAGE CREATE program, which is helping us to train other people how to make geological maps of the ocean floor. Most of you have seen our first map, which was created by Meg and a large group that's now been published in Geosphere. It's the 1 to 1 million scale geological map of the northern part of the Lau Basin. And we're currently working on two other maps, one in the adjacent North Fiji Basin and in Papua New Guinea. And each of those mapping projects is accompanied by what you would call metal earth type transects at about 1 to 1/4 million scale instead of 1 to 1 million scale. And these detailed maps are teaching us a huge amount about the crustal growth in the oceans in increments that are sometimes less than 100,000 years. And so we're doing that in a dozen different places at about 1 to 250,000 scale, many places within the Lau Basin, but also in other basins. And the first thing we learned, of course, is that not all of the crust in a simple arc-back-arc system like this is created equally. And that's coming out in all of the work, I think, that we're doing. Some of the quick conclusions that we've already talked about in previous partner meetings. I think the most important one is that the pulses of crustal growth that we've observed in the oceanic environment, they go hand in hand with a massive amount of plate fragmentation. And we're now looking specifically for the hallmarks of that process, the plate fragmentation, because the most important crust, or the most productive crust in terms of magmatic and hydrothermal activity in the oceans, at least, and probably in the geological record, really comprises these complex mosaics of microplates with countless triple junctions and other complex microplate boundaries that are really important for establishing crustal permeability for melts and for fluids. The main takeaway message is that every time you form a microplate, you form at least two triple junctions, and the crustal permeability associated with that is kind of profound. This results in a highly complex makeup for the back arc crust and intense crustal scale deformation. All of that is required to accommodate the growth, and I'll talk about that in a minute. And we think that these microplate breakouts are really the key to mineral endowment. So that's just a lot of words to say, and what you can see in simpler terms here in just a simple bathymetric map, which shows the really complex architecture of the well-endowed crust. You'll see the nature of the endowment in a minute. In the northern part of the Lau Basin, which is quite different from the less endowed crust associated with simple back arc accretion. The fabric is completely different, and this is a reflection of these microplate breakouts. And what we've been doing within the last year or so is trying to document the features that distinguish this type of crust from this type of crust. The first step, which was led by Meg, was the assemblage mapping, and which we can compare directly to greenstone belts at the scale of, for example, the Superior Province. And this assemblage mapping really was never done before in the oceans, and it was a real pioneering effort. In the Lau Basin, we mapped about 35 assemblages, shown here in these different colors. And at first we thought, oh, this is great because this is our map of a microplate breakout. But then it became clear that the assemblages and the microplates are rather different things. And it's probably a lesson for interpreting assemblages in greenstone belts as well. And I'll come back to that in a minute. In the Lau Basin, the boundaries of most of the assemblages, which would be the equivalent of assemblages, for example, in the Abitibi greenstone belt, most of those boundaries are stratigraphic contacts, they're conformable, whereas most of the microplate boundaries, which I'll show you in a minute, are structural. In fact, this is revealed in the reconstruction that was done by Alan Baxter a year or so ago, which shows the plate boundaries are dominated in the northern part of the Lau Basin, are dominated by spreading centers shown in red and these large transcurrent fault zones shown in different colors of orange. And they reflect a very deep structure penetrating basically to the mantle. I couldn't help thinking about some of these orthogonal relationships when we saw, I think on Monday, the deep gravity and resistivity structure of some of the greenstone belts. This architecture, many spreading centers, subparallel spreading centers, and large transcurrent fault zones accommodating that extension, basically opening simultaneously, are the hallmarks of hyperextension. The kinematics, this is just the same diagram with the plates colored in. The kinematics involve widespread microplate rotation and propagating rifts and accelerating and overlapping spreading centers and ridge jumps and fracture zones, and a really unbelievably complicated set of kinematic events. And this is a microplate factory. This is probably an analog, I think, of some of the well-endowed greenstone belts in the Superior Province. The major structures, they have to be large enough to accommodate the huge amounts of extension while remaining fixed above an upwelling mantle. And those structures can evolve rapidly. For example, in the case of the Lau extensional transform zone, from a purely extensional boundary to a transcurrent to a transtensional boundary to a purely strike slip boundary, all within less than a million years. And the same sort of thing is happening along a major step fault on the northern part of the microplate assemblage. So an important assemblage, or at least an important message here, is that all of these things are happening simultaneously, and that every structure is an early structure. You get a better sense of the relationship between the microplates and the assemblages on this map, which overlays the microplates, the colored plates, on top of the gray assemblages in the background. And you can see that the plate boundaries and the assemblage boundaries are not the same. The plate boundaries actually bisect the assemblages, and the individual microplates are actually made up of many slivers of different assemblages. So for example, the blue one here is the Nuafo'o microplate in the Northern Lao Basin, and it contains the elements of at least 10 different assemblages. And many of the microplates share assemblages on opposite sides of, for example, a spreading center shown here. And it's easy to imagine that with a small amount of crustal shortening in an arrangement like this, that you could actually bring many of these elements, these orthogonal elements, into essentially parallel arrangements that we're more familiar with in greenstone belts. It's in this way that the crustal makeup of the microplates can be really complicated and heterogeneous. It's no surprise to me that there's all kinds of inheritance going on with relic crustal fragments out in the middle of the back arc basins, with an extensive intrusion into the crust, even way in the middle of older back arc basins, and lots of intraplate volcanism and magmatism. And this is some of the work that we did a couple of years ago on our geophysical transects. Just to reinforce that, some new argon dating that's been done by Mark Fassbender, who's finishing up his PhD, reveals ages within a single assemblage, what we would have mapped as a single assemblage, ranging anywhere from 13,000 years to 10 million years in the space of a few tens of kilometers. Previously, we would have assigned all of this in the central part of the Lao Basin to one assemblage, but the age data show that the plate is clearly made up of many pieces of many different assemblages. This is something we've only come to grip with in the last year or so, really. We can also recognize that plate heterogeneity in exactly the same way we do in greenstone belts with geochemistry. And Mark has also taken a deep dive into machine learning, some of which is shown here, which compares felsic volcanic rocks in different environments. In this particular plot, the orange circles are the data from the Lao Basin. And the first thing it shows you is that they plot the felsic rocks plot in many different clusters. They plot in interoceanic back arc cluster, they plot in a volcanic arc cluster, and they plot even in a mid-ocean ridge type cluster. So the compositional variability within these domains is huge. There's also a highly variable and in some cases very important mantle input that's coincident with the microplate breakout in the northern part of the Lao Basin. And this is manifested in two ways. One, in helium isotopic compositions of basaltic rocks, but also in the water column, the helium plume above the northern part of the Lao Basin, which is reflecting the super intense hydrothermal and magmatic activity. The mantle signature in the rocks here is about 3 times larger than anywhere else in the basin, and the intensity of the helium plume in the water column is comparable really in intensity and size to the plume from the East Pacific Rise shown here, which is sourced from about 10 times the ridge length. We would expect something like this in an Archean greenstone belt, but it's a little unexpected in Western Pacific subduction zones. And basically the inference is interaction between a plume and the arc assemblage or the back arc crust, which is something that we've heard about, for example, in the Kidd Monroe, and more specifically at Kidd Creek. We're tapping mantle melt sources here that are producing enormous outpourings of mafic melt along what are referred to as the Rochambeau rifts here and the Northwest Lao Spreading Center, where several of our people are working. So the question was, can we distinguish these different types of basins like this in greenstone belts? And I think we've heard in the last couple of days that there are many attributes that we can look at that may help to do that. And some of it can be pretty simplistic. And this is an example comparing by the numbers the attributes of the northern Lao Basin, which we consider to be our endowed terrain, and a much larger and much less endowed North Fiji Basin. They've had very different evolution, and to the best of our knowledge, the North Fiji Basin actually is very poorly endowed in terms of magmatic and hydrothermal activity. The first thing you notice in the numbers here is that the Northeast Lao Basin is about half the size of the North Fiji Basin over here, but it contains about 11 different spreading centers compared to only 4 in the North Fiji Basin. The average length of those spreading centers in the Lao Basin is only about 139 kilometers, whereas the few spreading centers in the North Fiji Basin are much longer and opening much faster. So very, very different dynamic, which I'll touch on in a minute. Essentially, in this environment, in the Lao Basin, we have many small spreading centers or small rifts, subparallel, that are doing the same amount of work that a single large spreading center does in the North Fiji Basin. One of those two scenarios is better, or at least more favorable, for magmatic hydrothermal activity and mineral endowment. Can we see those things in greenstone belts? I think we're beginning to hear that, and in particular from the work that Taus has done. We can start by distinguishing something that we hadn't done previously. We can start maybe by distinguishing assemblages from microplates. So far, the focus is obviously on assemblages because they're easier to identify with geochronology and geochemistry. We might be able to identify deep structures that reach the mantle. I think that's certainly being observed in some of the geophysics, including early transcurrent faults that are needed to accommodate all of the extension in a productive basin. Maybe we can resolve higher densities of microplates. By density, I mean spatial density, not physical density, although maybe that too. And this information may be hidden in the deep resistivity and in the gravity anomalies. And maybe we can even identify optimal lengths or optimal spacing of spreading centers to encourage abundant magmatic and hydrothermal activity. And this ridge segmentation phenomenon is something that we already recognize from modern ridges as a control on melt distribution in modern spreading centers. And I think we can even distinguish between fast and slow spreading in ancient terrains. And this comes right out of area-age relationships, which are also going to fall out of the work that that Taus is doing. So those are boxes I think we can check when comparing modern volcanic belts in the oceans to greenstone belts. The microplate breakouts are key because they're linked to very specific far-field geodynamic influences, and those are highly episodic. So the microplate breakouts are the thing that's episodic within larger scale pulses of crustal growth, and this may explain why VMS deposits are confined to relatively narrow stratigraphic intervals compared to the long time spans for opening a large back arc basin. And in greenstone belts, the assemblages or the episodes, of course, have been pretty much nailed down. What's missing is our understanding of microplates. In the simplest configuration, the microplates are bound by big structures, but they're also probably stitched together by synvolcanic intrusions, which we've heard about already today. The result is that we're seeing in the modern microplates a very dense mosaic of structures that influence that result from this pulses of crustal growth, and it's far more granular than the assemblages that we have mapped in for example, the Lao Basin. And the question is whether that might also be true in a place in something like the Abitibi, where we have 7 assemblages, but maybe many more microplates. The question is, how do you identify those microplates? Certain structures are synonymous with microplate formation. One is triple junctions, like this one in the northern Lao Basin. This is a hallmark of a microplate breakout. And as I previously mentioned, it's a necessity or an essential outcome or geometrical requirement of microplate formation that every microplate produces at least 2 of these triple junctions. We should be able to find them. They're usually major centers of magmatic activity simply because there's more melt associated with 3 intersecting spreading centers than there is associated with just one spreading center. And a stable configuration like this in the Mangatolo triple junction, which we've been mapping, this can be stable for millions of years. We spent a lot of time, you spent a lot of time mapping in greenstone belts looking for things like calderas and half grabens, but I haven't heard anybody say definitively this is a triple junction. Microplate formation is also closely linked to rift propagation, another necessity. And we've been able to identify magmatic precursors for those events in the modern Lau Basin. And the question is, can we identify those sorts of magmatic precursors for rift propagation in the geological record as well? I'm sure there's a geochemical footprint. These propagating rifts, they produce melt corridors, which is what we see in greenstone belts that are hundreds of kilometers long and stitched with these subvolcanic intrusions. At the ends of these propagating rifts, there's often a deep hole. In this case, dropping from about 2,000 meters water depth down into about 3 kilometers water depth in the Fonolai rift system in the Lau Basin. And for those of you familiar with the Blake River, this would be like walking from the relatively shallow successions of Clifford Ben Nevis right into the deep cauldron of Noranda. These are the kinds of geomorphological features I think we need to be looking for. These grabens are everywhere in the modern arc and back arc environments, especially in on echelon arrays like this shown west of Tonga. And they reflect the regional transtension caused by widespread oblique collisions, which are the norm. Often these grabens are occupied by large shield volcanoes like this one in the Rochambeau Rifts, which is basically under the giant helium anomaly I showed you earlier related to a plume influence. So all of that is coming into focus now because we're mapping at 1 to 250,000 scale instead of 1 to 1 million scale. But I think we also have things to look for in greenstone belts that now, because we have this portfolio. There's an awful lot going on structurally, even within the assemblages that we've mapped. And we hope that where you can tease out a little bit more of this granular structure of the assemblages and the microplates from a closer look at the regional geophysics. We have just hired a new postdoc from Colin Farquharson's group, Chris Galley, who's going to be looking at some of the inversions of the regional gravity together with some ship-based gravity that we collected a couple of years ago to try and tease out more of the structure within these assemblages. Just to shift gears a bit, although we've been focusing on the Lau Basin and the oceanic domain, eventually these microplates and assemblages are amalgamated along more complex margins, and that's what we're looking at in the work in the easternmost Papua New Guinea. This is the 1 to 1 million map from PNG. The first thing you notice from that map is that there are many more assemblages here than even in the Lau Basin. I think as many as 38. And unlike the Lau Basin, those assemblages are mainly where the assemblages in the Lau Basin are mainly stratigraphic context. Here, the assemblages are mostly fault bounded. And in fact, everything that is mapped here is really just a fragment or a vestige of a microplate trapped between PNG and the Angtong Java Plateau. It seems likely to me anyway that the architecture of something like the Abitibi Greenstone Belt is going to fall somewhere in between a scenario like this where all of the microplates are fault bounded and something like the Lau Basin where many of them are splitting assemblages. One of the interesting things about this environment as well that is probably going to be relevant is that we've also been able to map out the development of a number of successor basins, which are indicated by the white arrows. At least 3 different types are all forming simultaneously. The sediment flux is huge because PNG is rising out of the ocean at about the same rate as sea level, or faster than sea level. So there's a huge offshore flux of sediment. Two of the basins here are the Western Bismarck and the Sepik Basin. These are on-lapping ocean, basically back arc or oceanic crusts. Another one here in the Solomon Arc in this beige color. Several older basins are associated with failed trenches, and there are at least two of these successor basins which are punctuated by alkaline volcanism, particularly in New Ireland and the westernmost part of the Bismarck archipelago. Any of these could be, in my mind, analogs for something like the Porcupine or Pontiac type sedimentary basins at about the right scale. And meanwhile, just on shore, you have Temiskaming conglomerates basically being deposited along major river systems like the Ramu Fault Zone here in the northern Papuan Peninsula and the Wayton Fault Zone in New Ireland. We hope we're going to have time in the project to look at these sedimentary basins in the next year. So just a couple more points to conclude regarding the comparison with greenstone belts in the Superior Province. In both cases, it's hard not to imagine some pretty simple causes of differential metal endowment at this scale, the scale of the Lau Province or the scale of the Superior Province, just from the abundance of volcanic rocks. And this is a very quick plot I put together just before this presentation, which basically spreads out the greenstone belts of the Superior Province in 50 million year increments. That's all of the greenstone belts in the Superior Province. And you can see that there's a clear step change at about 2750, which looks to represent accelerating growth, either as a result of faster spreading or, in my mind, more likely just more spreading centers. You can, of course, explain all of this away just by deeper erosion in the older terrains. But I would figure if preservation was the key here, was the only factor, you would expect a linear increase and not an acceleration in the area of greenstone terrains. You can also look at the rate of VMS formation in these different sub-provinces, which is shown here in the blue bars in terms of thousands of tons of massive sulfide per square kilometer of volcanic rock. And it's easy to see a 4 or 5 times increase in the endowment in the Abitibi compared to the other terrains. That may reflect the abundance of volcanic rocks, 2 to 3 times as much volcanic rock in the Abitibi as anywhere else in the Superior Province. That's obvious. But in addition to that, there's at least 100 times as much massive sulfide. That's a big difference. Even if you added in undiscovered massive sulfide deposits, maybe in places like the Ring of Fire, I think it's going to take a lot to upset this balance between 1 million tons and 825 million tons. You could account for this too by preservation, but you would have to selectively erode the most productive volcanic rocks in these older terrains to account for this difference in the abundance of VMS deposits. Or maybe you can explain it by more subaerial versus submarine volcanism, or very different geodynamics of the type that Keaton was talking about yesterday. Last slide here. We can also look at crustal growth even in the or any of the greenstone belts just by dividing the area of the volcanic rocks by their assigned assemblage ages. And doing this, you can see one clear thing, and that is that the crustal growth rates or inferred crustal growth rates for the Abitibi assemblages are way different from those in the Lau Basin, at least at first glance, from the crustal growth rates for the different assemblages that have been mapped in the Lau Basin. This could also be preservation, or maybe the difference is signaling different styles of crustal growth, which is where we're leaning. With the exception of Stoughton-Rochmauer, crustal growth in the Abitibi looks to be a lot slower than anywhere else in the Lau Basin, although maybe similar to the small orange bars here, which are the recent microplate breakout in the northern Lau Basin. By contrast, the less endowed crust in the southern Lau Basin, for example, is related to these huge bars of crustal growth, large amounts of back arc crust grown in a very short period of time. That statement is a bit counterintuitive because mineral deposits are supposed to be associated with these large episodes of crustal growth. But it's beginning to look like it depends more on the style or the type of crustal growth, how the crust grows, rather than necessarily how much of it grows. And I think possibly we're looking at a solution to that problem in the relatively slow growth rates of some of the assemblages in the Abitibi, like the slow growth rates of some of the microplates in the northern Lao Basin. This is the last slide. And just to reiterate that point, in a microplate mosaic like this, where you have many short parallel or subparallel spreading centers, you're able to accommodate a huge amount of basin opening, as much as you would with just a single large spreading center. The difference being that in a microplate mosaic, the cumulative length of all these spreading centers is much greater than a single spreading center occupying the same space, and with many more triple junctions, more propagating rifts, and more mineral deposits. Going forward, Alan Baxter is looking at exactly how this occurs in response to strain partitioning in the upper and maybe in the lower crust too, to establish how these large numbers of small plates emerge. And hopefully we can link that more closely to regional geophysics and this more granular view that appears to be emerging in the particularly in the regional gravity. So I don't know if I might have gone over there a little bit, but I'll stop now.
Great, thanks very much, Mark. Yeah, just perfect. We have time for one question. Bruno.
Great talk, Mark. My question is about like the chances, like a thin volcanic faults in the Abitibi is difficult enough to recognize because of overprinting and reactivation, later reactivation of the fault. How could we differentiate like a normal thin volcanic fault from a microplate boundaries? What are the kind of cue or evidence should we look for in the field to recognize a microplate boundary?
Yeah, that's basically the question we have going forward. We've only really just come to grips with the microplate architecture, and now we really do need to drill down on these contacts and these structures to answer precisely the question you've asked. Short answer is we don't know, but that's the goal going forward now. Get away from the volcanoes. I mean, that's what we've been mapping, right? I mean, they're the thing that everybody wants to look at. Get away from those a little bit and start looking at these structures that are required to accommodate growth. I think one of the things we have recognized is that there's an unbelievable amount of transcurrent and strike slip faulting at the very beginning. Like, the earliest structures are strike slip faults.
Thank you.
Okay. All right. Well, thanks everyone.